Glendale Community College, welcome back. This is our second video for Chapter 8 on acids and bases. So here's our next example problem because we love beaker drawings. So here's some generic beaker drawings with hydrogen and A minus. A can be anything. It's just the rest of the compound. So it's just a generic compound. So look at these four beakers. We have beaker A, B, C, and D. Look at them. Look at how some of them have HA together and some have H plus and A minus separated. So based on those drawings, which one is a strong acid? I hope you said beaker A because it's all ionized. We have all H plus A minus, H plus A minus, H plus A minus, etc. It's all ionized. That makes it strong. Remember, strong acids ionize 100% into ions. Ions have a charge. All right, which one of these beakers could be a weak acid? I hope you said C. C is the best example of a weak acid because we have mostly H and A still bonded together, HA, 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 and we only have one separated into H plus and A minus. So that's the best example of a weak acid. I suppose B would be a weak acid as well because it has a couple ionized and most of it is together, but C is really the best one. Okay, which, if any, is a strong base? I hope you said none of them. There's no hydroxide in any of these drawings. Bases produce hydroxide ions. Remember, we just learned that, OH minus. So I hope you said none of them. So what is D then? Well, it's just some neutral solution. There's no ions at all. So it's just some covalent neutral solution. It's not acidic or basic. All right, so I hope you did well on those. New topic, pH. The pH scale is something we use to measure acids and bases and what's neutral. The pH scale goes from 0 to 14, 0 to 14. 7 is right in the middle. Okay, so 7 is neutral. 7 is neutral. So as we go down from 7 towards 0, we're getting acidic. And as we go up from 7 towards 14, we're getting basic. Only 7.0 is neutral, not 6.9, not 7.1, but 7.0. That is neutral. Okay, when we're acidic, that means the concentration of hydrogen ions is greater than the concentration of the hydroxide ions. Those brackets around the H plus and the OH minus mean concentration of. So this means concentration of H plus is greater than concentration of hydroxide. And that's what we have when we're acidic. We have more H's because we're acidic, right? We have H's. Now when we're basic, we have more OH's because we're basic. So we have more OH's ions than the H plus ions. And they're equal when we're neutral at 7. H plus equals OH minus when we are neutral at pH 7. All right, I hope that made sense. All right, so again, those brackets mean concentration of. It's called molarity. We'll learn about that later. The unit is moles per liter. Moles is related to how many molecules there are. So a bigger number means more concentrated. So again, the concentration of H plus is the moles per liter of H plus ions. And if we're in pure water, H plus and OH minus are the same. They are equal because we're neutral. If H plus is greater than OH minus, the solution is, I hope you said acidic. If H plus is less than the hydroxide ion concentration? The solution is, and I hope you said basic. Good job. All right, where does pH come from? Well, it's actually a logarithmic measurement. Don't worry, we're not going to do log calculations. Let me show you how this works. pH is the negative log of the concentration of H+. So pH equals negative log of H+ concentration. Let's rearrange that, and we can get H+ equals 10 to the power of negative, and then the pH. So when we write it that way, pH is the exponent. So look over here. If the H+ is 10 to the minus 1, which is 0.1 moles per liter, the pH is 1. Again, that exponent is the pH when we write it as in this format. H+ equals 10 to the negative 1. 1 is the pH. That's it. The 1 is the pH. pH is 1. Is that acidic or basic? Acidic, right? pH of 1 is very acidic. Okay, what if the H+ concentration is 10 to the minus 5? Then the pH is, I hope you said 5. Is that acidic or basic? That's acidic, but not as acidic as 1. Okay, what if the H+ is 10 to the minus 8 moles per liter? Then the pH is, I hope you said 8. The pH is 8. Is that acidic or basic? Yeah, that's just a little bit basic. What if the H+ is 10 to the minus 3 moles per liter? The pH is 3, right? And that is acidic. Yeah. What if I write it this way? H+ equals 0.001. Well, we need to put that in 10 to the format. So if we have 0.001, we're moving the decimal 1, 2, 3 places to the right. So that's the same as 10 to the minus 3. So the pH would be 3. Very good. And now what if I write H+ equals 0.000000001? Well, let's move the decimal. We're moving the decimal 1, 2, 3, 4, 5, 6, 7, 8 places to the right. So that's 10 to the minus 8. So the pH is 8. Yeah. So again, when you write H+ equals 10 to the negative, and there's a number, that number is the pH. That number is the pH. Very good. Okay, great. You're going to see this more in lab. This is just for fun. pH is uncommon in materials. Vomit. Vomit has a pH around 1 to 2. It's really quite acidic. The acid in our stomach is hydrochloric acid. So it really burns your esophagus when you vomit, and it gets on your teeth, and it can erode the enamel on your teeth. So rinse your mouth out after you vomit. Of course, you don't want that taste in your mouth anyway. So yeah, rinse your mouth out with water. Lemon juice. Citrus juices are quite acidic, 2.3. That can also eat enamel off your teeth. Coffee. Coffee's around 5, so that's not too acidic. The spit in our mouth, saliva is around 7. Blood is right at 7.4, and that's important. If it gets too high or too low, you get alkalosis and acidosis and can die. Milk of magnesia is an antacid medication, so that's why it's basic at 10.5. Ammonia is a household cleaner, 11.7. Urine is around 6. Most sodas are around 2.5 to 3.5. That's acidic enough to erode the enamel on your teeth. Yeah. Root beers, in a way, it's not a cola. It's around 5.5. Buffers. A buffer is a solution that resists changing its pH, even if you add a little bit of acid or base to it. So it keeps the pH constant. This is very important in bodily fluids. Like we mentioned, our blood needs to stay right at around pH of 7.4, so our blood is heavily buffered. So even if there was a little acid added to our blood, it wouldn't change its pH very much. Even if you add a little base to it, it wouldn't change its pH very much. So what you need to remember here is that buffers resist changing in pH, so it keeps the pH fairly constant. And you'll do an experiment with this in lab. All right, let's draw some beaker drawings. You're going to draw a beaker drawing of HNO3. It has an H in front, so what kind of chemical is that? HF, it has an H in front, so what kind of chemical is that? KOH, it has an OH in it, so that should tell you what kind of chemical that is. And MgOH2. So I want you to draw little squares that are beakers of water. Draw 4 of them. And draw what you think HNO3, HF, KOH, and MgOH look like in those 4 beakers. I want you to hit pause and get out a piece of paper and draw these. It's the only way you're going to learn is if you do it yourself. So hit pause. Hit pause. Okay, we're back. So let's look at the answers. The HNO3 is an acid because it has an H in front. And that H pops off 100% because it's one of our strong acids. So the whole beaker should have ions in it. H plus, NO3 minus, H plus, NO3 minus, H plus, NO3 minus. The second beaker is hydrofluoric acid, which is a weak acid. So most of it stays together, HF. So we have several HF molecules. Only one of them ionizes into H plus and F minus. Weak acid. Then we have potassium hydroxide, KOH. That's a strong base, so 100% breaks apart. So we have K plus, OH minus, K plus, OH minus, K plus, OH minus. And then the last beaker is a weak acid, magnesium hydroxide. So most of it sinks to the bottom. So you should have a little squiggly line at the bottom with the MgOH2 down there. And then just draw one of them broken apart into Mg, which is a +2 charge. So we need 2 hydroxides to balance that out, OH minus, OH minus. Okay, I hope you did good with these beaker drawings. It's very important that you can draw beaker drawings in this chapter. So summary, so far in chapter 8, Arrhenius acids make H plus ions in water. Arrhenius bases make hydroxide ions in water. Bronsted-Lowry acids lose an H plus. Bronsted-Lowry bases gain that H plus. Strong acids ionize 100%. Weak acids ionize way less, 1 to 5%. Strong bases dissociate 100%. Weak bases dissociate way less at 1 to 5%. And buffers keep the pH fairly constant. All right, that's a great place to stop for this video. In chapter 8, we'll continue in our next video. Bye, GCC.